Hello, everybody, and a warm welcome to the first in our series of Nuclear Masterclass webinars. It's great to see so many of you joining us live. I think the number's at 280 at the moment, will probably creep up over the next few minutes, so welcome to everybody as you're coming in. I'm Dr. Elizabeth Cunningham. I'm a former nuclear physicist, currently science communicator and Lego enthusiast, and I'm very happy to be here tonight to chair what I'm sure is going to be a fascinating webinar. And we are in for a great treat tonight because our speaker is the fantastic Dr. Christian Diget. So Christian is a lecturer at the University of York and academic lead on binding blocks. He's originally from Denmark. I don't know if it's compulsory if you're from Denmark to be a fanatic of Lego, but he is, and that's why he set this whole project up around Lego. He's an experimental nuclear physicist, and his research focuses on understanding nuclear reactions in exploding stars. And if that wasn't enough, he's also developing new cancer therapies based on radioactive nuclear isotopes. Tonight, Christian will be exploring how atomic nuclei are made, discovering the properties of the building blocks of the universe, and investigating how the many and varied isotopes are critical to our daily lives. So not bad for a Wednesday evening. All that's left for me now to do is to hand over to Christian and enjoy this webinar to everybody.
Thank you. Thank you very much, Elizabeth. It's great to be here, and it's great to be back in the masterclass setting. It's great to give a webinar to you. Thank you so much again, just as Elizabeth said, for joining us. It's very nice to be able to share all of this with you. So today, as was said, the focus is on nuclei, on atoms, and what that means. So I've titled it From Atoms to Alchemy, and the focus will be on where do nuclei come from, and what can we use them for. And as you might know, alchemy is about converting one type of material to another, and actually it's quite interesting that that is part of what we do, both what the universe does for us, but also what we do artificially in nuclear physics in order to make some of the material that we can use for other purposes, such as nuclear medicine. I will touch briefly on that as well as we go along, but there's more on that later in the series. To get started, make sure that we start in the same place, all of us. You may have seen the periodic table before of chemical elements, ranging from hydrogen to most recently organeson as the highest element. This periodic table, I can warmly recommend it. It's from Royal Society of Chemistry, and you can see some details of a number of different elements when you click on them. So that's quite nice. One of the things that you see if you click on the elements here is that you see, for example, that you see their chemical mass, and actually the chemical mass, even just the chemical mass within the standard periodic table, tells us a lot of the nuclear physics, in fact. So you can see here that fluorine has a chemical mass of about 19. Magnesium has a chemical mass of about 24.3. Now, the 19 is because there's 19 subatomic particles, 19 nuclear particles, protons and neutrons put together inside the nucleus of the atom. So the fact that there's 19 actually is exactly accounting of how many nucleons are there put together. So, but if that's the case, how could magnesium have 24.3, right? It doesn't have 0.3 of a proton or a neutron. It must come from somewhere else. And the reason for that is that there's more than one type of magnesium. We call those isotopes because they're of the same type of material. And you can probably guess that there's a lot of magnesium 24, so with 24 total protons and neutrons. And there's a little bit of those that are slightly heavier, naturally occurring around us, in us. It's what we're made of. So there's a little bit of 26 and a tiny bit of 25 as well. So in addition to that, those are just the naturally abundant isotopes, but there's more to it, and that's where the majority of the front end nuclear physics that's going on at the moment is taking place. And I'll come back to that in just a moment when I've said a little bit more about the atom, how that's built, and what the relevant scales are. Right. So I've already indicated that there's something in the center of the atom. It's called the nucleus, and it has protons and neutrons in it. It has electrons around it. It is actually much of an electron cloud, but you might have seen it as kind of rings of electrons. That also has some truth to it, because the electrons kind of congregate in shells as you build it up. The electrons can't be in the same, we call it quantum state, the same quantum state as the other electrons. So as you fill up more and more electrons in the atom, you actually fill up different quantum states further and further out at higher and higher energy. So we have this kind of electron cloud. But what we're focusing on right now is not so much that cloud of building up electron states, but what's going on right at the center of the atom, and that's where the nucleus appears. I've indicated it here, but it's completely off scale, and I will say that in a moment. We have to zoom in on that. And the reason for that is because of the scale difference. So it's about a factor of 100,000 between the size of the atom and the size of the nucleus, right? So if you can see the size of the atom, you cannot see the size of the nucleus. You can't see it on the same picture, in effect, right? But just to give a sense of scale, right? Let's say I'm about a meter diameter, down by a factor of 100,000 is roughly one of my cells in, let's say, my skin here. One cell within my skin is approximately a factor of 100,000 smaller in each of the three directions than I am. Right? Within that cell, there are a lot of atoms. In fact, the atoms are about a factor of 100,000 smaller in each direction compared to my human cells. And within that atom is the nucleus, and again, is about that factor of 100,000 smaller. So think of the nucleus as having about the same size relative to the atom that each of my cells have relative to me. So let's move on. We talked about atoms, and you've seen how we can have different, what we call isotopes, some that have the same element properties, they're the same chemical element, but they have different properties inside the nucleus. And the way we represent that normally is that we represent each isotope, each element, as a line, and along each line, so this line, for example, is carbon isotopes, along each line, horizontal line in our chart of nuclides, we present the different isotopes, the different ways that the nucleus can have been put together. So for carbon, the stable ones are carbon-12 and carbon-13. I'll come back to the carbon-12 because I did a lot of work on carbon-12. But we've also got other options of carbon-12 here. They're those that have fewer neutrons attached to the inside the nucleus. So there's the same number of protons in this case, because the protons inside the nucleus is what defines the element, defines how many electrons there are, and the electrons define the chemistry. The number of neutrons define what is the nuclear property inside that atom. You can also see now that there are a lot of them, right? So each row, now if we look at the total chart, each row is one of these 118 elements. In fact, it goes beyond, because this is just it could go even further than that, is what I mean. The stable ones are the black ones, and everything that's colored decays in one way or another. You can come back to how the different decays are, but alpha decay, beta decay, and fission as well. So that's how we structure the nuclear chart. And what we find is that the different isotopes have different properties and they have different energy, they have different decay types. The decays typically happen and for nuclei that have too much energy, and they get rid of that energy by decaying one way or another. So let's take a look a little bit more at how we make these elements, how we make these new isotopes. So one of the first cases of this was actually by firing alpha particles, helium nuclei, firing those at a gas, at a nitrogen gas. So this is nitrogen 14, it's natural nitrogen. And what they found, and this is back in the first time in 2019 by Rutherford, and subsequently by Blackhead, where they could study the reaction in more detail. They could then hit the nitrogen with an alpha particle, and they could see that they produce protons. So if they produce protons, it means that something is happening, right? They didn't have protons before, they now have protons. And what they could show was that they were actually transforming nitrogen into oxygen. So instead of having an alpha particle or a helium, they ended up having hydrogen. And in that process, they've moved one of the protons from the target, the nitrogen, into the oxygen instead, into the nitrogen, which has now become oxygen. Right. So what they've done is actually what in the old days were anticipated as alchemy, where people tried to change one material into another. This is changing one material into another, in this case, nitrogen into oxygen. In fact, Rutherford said, don't call it transmutation. They'll have our heads off as alchemists. It was partly to, I think, explain how ridiculous this idea is, that actually you can change the material, and we can do that. We can control it. We can decide what we want to make. And that is indeed what we do now. So one example of this is from one of our detectors. This is the gas detector where we see, it's called a cloud chamber, and indeed we can see these sort of whiffs of cloud that actually appears in our chamber as individual particles travel through the material here. This was the type of measurement that actually was done back in 1924. But because these nuclear reactions are rare, they had to look at, kid you not, 400,000 tracks in order to see 8 reactions, right? Now, nowadays we do this in automated digital systems that record the data and we can process it on a computer. It's much, much easier. There was a lot of craftsmanship involved in that back then. So what is it that happens in this process, right? So in order to understand that, I'll say a few words about binding energy. The main point in nuclear physics is that if you've got, let's say, a proton and a neutron, like these, and you put them together, they stick, right? So if the nucleus is bound, which all of the nuclei that I will show today, they're bound. If they stick together, it's because they're bound together, and they do that with a binding energy. So when you put them together, they stick. It takes energy to pull them back apart, right? So first question would be, how much does it take to pull them apart? I've got these two stuck together with Velcro. You can try to assess how hard is it to pull them apart like this. We can talk about that in a moment, in a little bit more detail. Just think about how would you even assess how much that takes. We do that in nuclear physics in other ways, but how would you do it if you had two things that were stuck together and you wanted to see how much it takes to pull them apart? So when we put these two together, they attach to each other. They're bound by binding energy. It means that their energy is a little bit smaller. It also means that their mass is a little bit smaller, because mass is energy. And I'll come back to the scales of that in just a moment. So I've got this illustration of it here on the screen. where you can see, okay, let's imagine that this is the energy they've got when they are separate. If we put them together, they have slightly smaller energy. It costs energy to take them apart again. That process is disintegrating it into its protons and neutrons, and the difference in energy is the binding energy. And what I show here is that you can have different binding energy depending on the nucleus. And one of the ones that's by far that has a particularly strong binding energy is helium, the alpha particle. That's why it appears in alpha decays. And what that means is that it's much more preferable to put these four together than just putting them together two and two. So to summarize that, it means that deuterium, which is one neutron, one proton, it has less energy than they have separately. And the helium has even less energy than those four would have had otherwise. What that means is that the helium now is lighter, it has less mass than those four would have had separately. So how much is that, right? We can see here how much energy it takes to pull them apart. I would say that probably takes the same as lifting about 100 grams, and it'd probably be over about a centimeter. So I could calculate how much energy does that force times distance equate to. I would say in this particular case, I would say it's probably about 0.01 joule. In comparison, if you have something that's 1 kilogram and you drop it by 1 meter, that's about 10 joules. Okay, so that's the sense of scale. In my example here, it would cost about 1,000th of that. It makes sense. There's a little bit of energy involved in that. If you throw a massive book on the floor, it gives much higher of a sound, right? So let's take a look at the energies involved in nuclear physics, right? Well, nuclear energy, we can get it from Einstein's formula, E equals mc squared. If you haven't seen it before, you've definitely seen it now. E equals mc squared. It means that something that's massive has more energy intrinsically bound in that mass. So it's independent of whether it moves or not. It's just their intrinsic energy because they have mass, right? And you can get the mass, you can get it in joules if you calculate it using SI units. Let's say we have 1 kilogram of material, like the 1 kilogram I was dropping. We can get it in joules if we multiply that by the speed of light, c squared. C is a very big number. It's 3 times 10 to the 8. So you get 9 times 10 to the 16. So 9 with 16 zeros behind it. And let's see, 1, 2, 3, 4, 5 times 3, that's 15 and 1. So yeah, I got the number of zeros right here. We've got 90 million billion joules of energy encapsulated in just the mass of something that weighs 1 kilo. So let's say 1 kilogram of water, 1 liter of water, right? Now, it is not all of that energy that we can convert when we, for example, attach or detach nuclei, or if we combine it into helium, but we can convert something of order up to, let's say, 1% of its mass, right? 1% of such a big number is still a big number. So it still means that you get a lot of energy out of it. And just to give you a sense of it, even just water, I've got a little bit of water in this. Even just 1 liter of water, if you take the little bit of special hydrogen, that's deuterium, you pull it out of that water and you imagine that you could fuse that into helium, you would get about 15 gigajoule, 15 billion joules out of that. That's approximately the same as my electricity consumption, including all of the UK factories and other services that support me, right? So it's my proportional usage of electricity per year, right? So if you imagine just taking that 1 liter of water out of the sea, taking the little bit of deuterium that's in it and converting that to energy, that's what you'd get. This is why nuclear energy is significant, and it is part of our resources at the moment. So, coming to the sort of research area that I have been involved in, one of these reactions is combining helium atoms or combining helium nuclei to carbon. It happens in stars. And in fact, this is one of the few cases, if not the only case, where a stellar observation determined or gave rise to a nuclear physics conclusion, because Fred Hoyle managed to persuade people to look for a specific type of quantum state in carbon, because he said, well, if it's not there, then we can't explain the amount of carbon and oxygen that we observe in the universe. So there must be this kind of state in carbon. And they went and looked for it, and indeed they found it. I did quite a lot of my work on states that are related to this, so it's very dear to my heart. And I did those experiments by studying them not in those reactions, but reversely, where we populated them in beta decays. So we let another isotope decay to carbon. That gave us enough energy within the carbon system in order for it to break up into helium particles, alpha particles. And by measuring those, we could study what is the detailed structure of these particular states in carbon. And from that, how does that then affect carbon production in the universe? So that was actually my my thesis work when I studied. So there are other ways, though, that we can make elements that are not just fusion of, for example, protons or alpha particles, as for carbon. We can also, if we have an environment where there's a lot of neutrons, we can actually do this thing where you take an isotope, you add on neutrons, so you move along we call it the isotopic chain, because we add neutrons, so it's still the same element. You could take uranium, or you could take iron, right? So we take iron, we have one naturally occurring iron atom, and we put it in this intense bath of neutrons. It gets hit by neutrons all the time, and eventually it'll absorb one. It becomes the next iron isotope. It absorbs another, it becomes the next one. It absorbs another, it becomes the next one. And it does that until it starts beta decaying, and you get repeated beta decays that convert the neutrons to protons, and we move up the chain of elements to the heavier elements, to the heavier nuclei. And we repeatedly absorb neutrons. So that keeps going until we end at the top end of the nuclear chart that I showed you before, with the very heaviest elements, such as uranium and in the vicinity of that. Eventually it stops, because they start emitting alpha particles, or even fissioning when we get way up there. But this is actually how about half of the material of the very heaviest elements, this is how they're produced. They're produced in very intense neutron scenarios. You might hear more about that next week. These are called neutron stars. And when they collide, they can actually change isotopes from one to the other, and even make the heaviest elements. But what if we want to go beyond what is possible around us in the universe? Actually, we do that nowadays in nuclear physics. We go beyond what is even possible in stars. We call those super heavy elements because they are beyond what can be done building heavy elements in the universe. And the way these can be produced is if we take something that's very heavy. Lead is the heaviest that we have naturally occurring, at least in abundance. And we match that we throw a beam of something that's reasonably heavy onto it, and we let them fuse, and we look for products that come out of that. So again, the same type of nuclear reaction. We smash two things together, smash nuclei together, and we observe what's coming out of it. And the way that this is done is in a big accelerator with massive separators at the end, where we can separate out, okay, this is one product, this is another product, and we observe how much we're producing of each. So this is how the very heaviest elements were produced. This, what I'm showing here, is an example of the production of what's called now darmstadtium. It was discovered, perhaps unsurprising, in Darmstadt, and that's why it's called darmstadtium. And it was produced by this type of reaction, smashing two heavy things together, and observing a sequence of alpha decays out of that. And it does that until something else happens. For example, if it ends up fissioning, then it produces two nuclei, and we can't really tell the difference between those. But if we have alpha decays, and I'll show you that now, we can tell the difference between one isotope and another from their decay chain. Because the decay chain is very unique to each isotope. So this is one example with this darmstadtium isotope, where you can see that, well, from darmstadtium, you have 1, 2, 3, well, at least 4, in some cases 5 alpha decays subsequent to each other. And if you know what their energies are, and if you know what their half-life is, how quickly they decay, then you've got this sort of unique fingerprint of this is the chain, and therefore this was our original isotope. And the reason why that's unique is because each of them have a unique energy within their nuclei, and therefore the energy difference between those available to the decay is given from Einstein's E equals mc squared, is the energy that is emitted, and we observe it in that alpha decay. So that's what we're looking for when we look for these types of extremely heavy elements. The most recent 3 that have been discovered in recent, or 3 of the most recent ones in recent years, have been darmstadtium, nihonium, and oganesson. From the periodic table, I don't know if you spotted that way at the start, the periodic table now seems quite complete. And the reason for that is that oganesson matches as the final element. Okay, does that automatically. It's the final element of its row, and that is the noble gas. It is in the noble gas column of the periodic table. So we think that oganesson is a noble gas. At least it should match as a noble gas. But because there's so few individual atoms that have actually been detected of the type of the element oganesson, we haven't actually, to my knowledge, measured yet that it operates chemically as a noble gas. But maybe that's something for one of you to do in future years. I think that would be really exciting if we could actually see the chemistry of these. And there is chemistry done at the individual atom level nowadays on isotopes that are produced artificially through nuclear reactions. Another way we can use these isotopes, or that we can use this way of producing nuclear isotopes, is that we can use them for medicine. Now, again, there's another session in a few weeks' time that dives much more detailed into medical physics, but we can create them. One of the pioneers in this is Lise Meitner, whom I'm showing over here. This is from a picture from around the time she did her PhD in physics, and we can make these elements if we can first produce them. Nowadays, we produce them in nuclear reactions. In all cases, they would typically have to be chemically separated, and a lot of Lise Meitner's work was on the chemical separation of these radioisotopes. Radioisotopes because they were radioactive isotopes, We produce these radioisotopes for medicines. There are different reasons we could do that. We could do it for diagnostics, but we could actually also do it for treatment. So one of the aspects that we've talked about so far is nuclear energies are huge, right? So there's a lot of energy stored in the atom, stored inside the nucleus. What could we do? What if we could take that energy and dump it into a cancer cell such that we could kill the cancer cell with the energy from the nucleus, from the nuclear decay? And actually, that's one of the things that's going on at the moment in nuclear physics, and I'm super excited about it because it's a type of radiation treatment where you dump the radiation locally inside the cell, because actually these alpha particles that I showed is emitted in alpha decays. These alpha particles, they have a very short range. They only travel a few cells within the body. So if we could deposit them inside the cancer cell, that would be super exciting. There's much more to talk about in relation to that in the coming weeks, and I won't go into all of the details, but just say this is, from my perspective, one of the super exciting aspects of nuclear applications that we're looking at the moment. One such isotope is called actinium. We call actinium, well, the element is called actinium. The isotope that we particularly look at using is actinium-225. There are other isotopes that could be used for alpha therapy. But actinium is interesting from one perspective in that it actually decays through a similar chain of alpha particles, in this case 4 alpha particles. And all of those, of course, could potentially bring their destructive power to the cancer cells in question. So the key for that, of course, is we need to produce the isotopes and we need to produce the pharmaceuticals that can deliver the destructive power directly and specifically to the cancer cells. So that's where the modern research in that type of treatment is ongoing. I do that kind of research at a facility called Triumph in Vancouver. So I've got a little bit of a picture of Vancouver in the background here. As you see it, the picture below that is the Triumph cyclotron. To give you a sense of scale, the white dot, I don't know if you can see, that depends a bit on your screen resolution. The white dot in the middle here is a person managing or replacing elements in the cyclotron during a shutdown. So here the cyclotron has been lifted open and someone has walked in, climbed in, and is currently repairing components inside the cyclotron. That's the cyclotron that actually has been used over the past years to produce actinium as one of the few accelerator-produced actinium accelerators that produce actinium. So with that, just to round it off, I hope you've got some excitement about the different ways that radioactive decay can be used in stars and in our galaxy, and for diagnostics and cancer treatment, and have a sense of how this massive energy and power output can come from nuclear physics. There's much more about those 3 areas in the coming weeks. There's a devoted session to each of them. But for now, this is what I wanted to share with you. And I'd be very happy to answer your questions. So please bombard us with your questions. We'll do our best to get through as many of those as possible. Thank you so much.
Well, thank you, Christian. That was a wonderful talk. You did an amazing job introducing at the beginning the key concepts that people are going to need for the whole nuclear masterclass, and then segueing to the really cutting edge and exciting science that people are researching now. So thank you very much for that. You're obviously very engaging because we've had questions posed all throughout the talk.
Excellent.
So
That's great. Great to hear.
yeah, I will start with an early one. So how can you fire alpha particles without electrons, or are they fired with electrons? I think that's referencing one of your early slides.
Yeah, so in that case, actually, this was for the very early experiments. In those experiments, the alpha particles would come from alpha decay. But actually, when the alpha particles move out in the decay, they move too fast for the electrons actually to catch up with them. So actually, they would normally fly as alpha particles and not as helium. And it's the same thing when we accelerate. If we accelerate alpha particles, we would typically also do that certainly as ions, but we can produce them with either no electrons or one electron on them. And in either case, they can still be accelerated. So it's quite a bit of an art to figuring out for a specific accelerator is one configuration or another most optimal. And they have some fancy stuff at Triumph that I could talk for days about. But yeah, let's leave it at that. I hope that answers your question. Yeah.
Wonderful, thank you very much. We have another question about different quantum states of an electrons in an atom, and
Yeah.
do the different quantum states affect the creation of isotopes in any way? If so, in which way?
Yeah, so the quantum states of the atom do not really affect the production of the different isotopes. So the isotopes is about what the core of the atom does with the protons and neutrons. The quantum states around it with that I talked about there are the electrons. Um, but actually, there are quantum states also inside the nucleus. And indeed, the protons and the neutrons find their own quantum states inside the nucleus. And I think there are a lot of similarities between those quantum states and the quantum states of the electron system. But I think for now, I'll leave it at that. But you might hear more about quantum states in nuclear systems next week. Yeah.
Okay, thank you very much. This is an interesting question about protons and neutrons if they're traveling really fast. So are there any relativistic effects on mass of nuclei if the protons and neutrons are traveling very fast?
So there is in the sense of the reactions that we do need to take into account the relativistic energy of the nuclei as we shoot them at each other. I work in because a lot of my work is in isotope production in astrophysics, for example, where the energies are relatively low, so our particles are not particularly relativistic. They might only travel at 10% of the speed of light, where the relativistic effects are moderate. But in some cases, there are many experiments where the particles travel at 90% of the speed of light. And in those cases, the effects are very substantial on the energy that they collide with. Right.
Okay, thank you. We've got loads of questions coming in, so I'm just trying to group them up. Someone has asked the interesting question of, is it possible to predict the decay chain of any isotope before creating it?
So you can say a lot about its likely decay based on where it is in the nuclear chart. I don't know if you remember the chart that I showed you, it has all of the stable elements were drawn in black, and the two sides were clearly differently colored, right? That's because decays always go, in a sense, in terms of energy, it always goes downhill, right? The decays are there in part to release energy. So you go from a high energy state to a low energy state. And which direction, which type of decays goes towards lower energy is quite easily predictable, right? So, but then there are all the details of when two of them compete with each other, that's when it gets really tricky, right? The overarching picture of everything decays towards stability. So if we are on the side that have too many neutrons, there will be a beta decay that converts neutrons into protons in order to get closer to stability. If we're very high up in mass, there's an energy advantage of emitting alpha particles. So that is what generally happens. There's also an advantage in having fission happening and having it split into two. The competition between fission and alpha decay is very complicated up at the high end. So if you look at that another time, or if you go back and revisit this lecture, try to look out for how scattered the green fission and yellow alpha decay is up the very top end of the nuclear chart. And you'll see that they're really just like mixed in with each other. And that's because the competition between alpha decay and fission is quite complex. Yeah.
Okay, thank you very much. There's a lot of interest in sort of the limits of existence. So what is the limit to the maximum sort of size that elements can get to? What is so interesting about the island of stability? Are we going to get there? Those sorts of questions about
The
the limits
first,
of.
I will give more than one answer. The first and most honest answer is nobody knows, right? That is an honest answer because we can't reach it experimentally, and because there are, depending on the theoretical model, you do make significant predictions about things that go beyond where we can currently reach experimentally, right? So you've probably guessed that I'm an experimentalist by now. So I do take those models with a grain of salt, right? They all agree that just beyond where we can currently reach experimentally, there's a region of the nuclear chart, and this is why some will have heard of the island of stability. There is a region of the nuclear chart where, depending on which model you use, you get a region that is of isotopes that is either actually stable or are almost stable, have much longer lifetimes. The decays of, for example, damstatium and organesson that I talked about are super quick, microseconds, that sort of scale. So a millionth of a second, for example, or even shorter in some cases. The lifetimes of some nuclei beyond that could actually be substantially longer, and in some cases might even be stable. We can't currently reach it because it's very hard to combine those types of isotopes together. I showed you one example of that sort of collision. But in that particular collision, there are not enough neutrons in order to reach the island of stability. So in order to do this, we would have to create a very intense beam of radioactive isotopes that have way more neutrons than is naturally occurring and than is, if you wish, normal or preferable. And you'd have to smash that into a target that already has a lot of neutrons. So it is, we can talk about now realistic experiments, but they're still very hard to do, and it would require new facilities in order to reach that island of stability. Yeah.
Okay, thank you. So there's also lots of interest, I think, now in the super heavy elements. So there's questions around how do you know that you've discovered a new element? Do you see a new number of protons or neutrons?
Yeah.
Why are there so few atoms produced when these new elements are produced? Could we ever produce enough for it to be useful? Could there ever be any uses of these sort of super heavy elements that we produce so few of?
So I think the first answer is there's so few produced because those nuclear reactions are rare. It's very hard to get those two to attach because you have to give them a lot of energy in order for them to attach, which means that there's a lot of energy available within that combined system. And it means that it's very likely that that system either breaks apart or spits out so many particles that you haven't got enough for having produced such a super heavy element. You need to combine them, and for there to be only one or two excess protons or neutrons that are emitted in that process. So that's a very hard process to do. It's very unlikely, and that's why you need. So these experiments, they run for months, and they get like 2 counts in half a year. Right. So So that's why. So that this is why there are so few of them produced. It's because the reactions are extremely difficult to do. It's extremely unlikely. It is possible, and therefore you can do it if you run your beam together on your target for long enough. So that's the why is it so difficult, and why are there so few? It also answers that probably this means that we won't be able to use those on a day-to-day basis because they're so hard to produce. What they do is that they give us a much better understanding of that region of isotopes, which has a lot of similarities with, for example, the actinium region that I talked about before. So there's a lot of better understanding. It might be that we can better predict alternative medical isotopes, for example, if we understand that region, better. Yeah.
Okay, and how do you know you've discovered a new element if you
Yeah.
discover it?
Okay. I knew there was another part to the question. Thank you. So the way that it happens is that um they fire them together. The combined isotope keeps moving, and this is they're fired together at relativistic energies, so they keep moving. Um, the product keeps moving ahead, and then there's a separator out there that separates one isotope from another. Now that's still so we know a lot then after the separator. We know a lot about what type of isotope it could be, but it's still not quite enough. We know something about its mass, for example, um, but we only know some limits to mass and element number. What we really need is that fingerprint I was talking about, measuring a decay chain, right? And measuring a decay chain until it hits an already known decay chain is the key. So if you already know, okay, these decays come from this nucleus, when they come in this succession at these energies, you can then trace it back to say, okay, now we have one that emitted two alpha particles first, and then it hit this known decay chain. So you kind of build it up from the known isotopes. And this is also why this is also a complication of even if you can, when you can produce, for example, isotopes in the region that you talked about before, of the island of stability, or so called, if they are stable, they wouldn't decay. And therefore, we would have to have completely different techniques for identifying them rather than the techniques that we use nowadays, because we rely on their radioactive decay. It doesn't happen if they're stable. So, and it's not good enough if they're very long lived either. So we would have to have new detection mechanisms as well.
Okay, thank you. Somebody has asked, or two people have asked for more clarification around the cyclotron. So a bit
Yeah.
more information about what a
Yeah.
cyclotron is and how it accelerates particles.
Yeah. Okay. So in an electromagnetic accelerator, if you have just a difference between voltage of let's say two plates, that gives an accelerator. And if you have an ion in between, that will accelerate towards the plate that it's attracted by, right? So that is the fundamentals of accelerating nuclear particles, right? The trick is you need to do this repeatedly because we want to accelerate them to very high energies. So the way we do this is that actually we produce, instead of having just two plates that it moves from one plate to another, it hits it, or it hits a hole and it goes through. Instead of doing that, we create an electromagnetic wave. So think of a surfer that's surfing on a wave in the sea. The reason why they're pushed forward is because gravity is pushing them down and the wave is pushing them forward. It's the combination of gravity and the wave. Now, gravity is not a player in accelerating protons, for example, but there's still the effect of there's an electromagnetic wave. And if you are riding just on the wavefront of that wave, and the electromagnetic wave is moving this way, then you're accelerating the particle that way. So the electromagnetic wave creates that electric field that can accelerate it. So actually, these are radio wave accelerators. The way the cyclotron works now is you have this traveling wave, but it travels between, you create that sort of gap in, you create that acceleration at times in a cyclic motion. And you make the particle bend around in a magnetic field. And then at times along that cyclic motion, you accelerate it more and more and more. So you go through many, many acceleration stages as it's traveling around the cyclotron. I hope that explains it. It was a bit of a long-winded explanation. I appreciate that. But I think I had to go back to the basics of the acceleration. In the end, it's you start in the middle and you accelerate, and the more you accelerate, the harder it is to bend, and the bigger the cyclotron motion is. And in the end, you exit the cyclotron and you go into the experimental hall or hit the target where we want to reduce the medical isotopes. Yeah.
Very good. A couple of people have asked actually about careers and what
Yeah.
grades what subjects do you need to study to get a job in this, and
Yeah.
how did you get a job like this? Like, people would love to work in particle accelerators. Are there any
Yeah.
tips? What
Yeah.
was your experience at Triumph like? And if you could do an MPhys, what would you do past that? Would you have to do a PhD and those sorts of things?
Yeah, so I did a bachelor's degree and a master's degree and a PhD, and that's how I got here. I started off with a focus on particularly mathematics and physics. I came from a very broad A-level equivalent background. My Danish studies were very broad. I did A-level equivalent in Danish literature, history, mathematics and physics, and I had English and German and many other topics at lower levels as well. So I actually came in with quite a broad background. I find that to be very positive. I think I learned a lot about communicating science by having that sort of broader perspective. The sort of core topics that I use on a day-to-day basis, and that's critical in studying physics, are particularly mathematics and physics. So those two are absolutely critical, and I use that obviously on a day-to-day basis. I'm a bit extra biased because I also then entered a mathematics and physics dual degree program back in Denmark. And then subsequent to that moved in a direction of physics. Yeah.
Very good, thank you. There's a few people who are perplexed by the fact that you can have really large isotopes that are stable, even though there's lots of protons in the nucleus, which should then, in theory, repel each other.
Yeah.
And then the element, so you can have a stable element, and then the element right next to it is really unstable and decays really quickly.
Yeah.
So how does that happen?
Yeah, I completely agree that is somewhat perplexing. So the first thing to note is that the protons, they repel each other, but they do also attract each other. If they're close enough, they do also attract each other. They just don't attract each other quite enough. They need something else that's also helps attracting, and that's the neutrons, right? So if you just had the two protons here, they would fly apart, right? This would be hydrogen 2. Hydrogen, because the two protons, they would still fly off from each other. You need at least one neutron in order to bind them together, right? So this would be helium. Sorry, this would have been helium. Sorry, did I say hydrogen? This would be helium 2, helium 3. The alpha particle was helium 4, right? And you need more neutrons the more protons you have. So typically, as a rule of thumb, if you put the same number of protons and neutrons, you're not far off. But the heavier you go, the more the repulsion starts to dominate. And the more the repulsion starts to dominate, the more you need to spread out the protons, get them a little bit further away from each other with extra neutrons, get the binding a little bit tighter with the extra neutrons. So that's the global picture. That's why actually, if you look back to the nuclear chart, you'll see that it bends a little bit to the right. In terms of the other effects, there are other effects that are really quantum effects that involve why some isotopes or elements are better bound than others. And you can get these weird effects where odd, for example, that odd element, there's an odd element that doesn't have anything that's stable. For example, technetium has no stable elements, have no stable isotopes at all, whereas the two neighboring elements have plenty of stable isotopes. And that's because there are quantum effects involved that two protons or two neutrons are particularly attracted to each other when they come in pairs. This is also part of the reason why the helium nucleus is particularly well bound, because it's a perfect double pair in that sense.
Okay, thank you very much. Back to super heavy elements again.
Mm-hmm.
So if super heavy elements are so short-lived, how do we detect them? How do we know that they were produced? What technology do we use?
Mm-hmm.
And how do you do any, if an element is such a short half-life, how do you do any research on it? Can you get chemical properties?
So the first thing is you make use of them being super relativistic, because it means that even though they're super short-lived, they can still get from where they're produced through the separator and hit a detector, right? So they're actually embedded in a detector tens of meters further down the tunnel. That detector is now sensitive both to the impact of the first one and also to the subsequent decays. So you know exactly where it was embedded in your detector, and then you detect the first implantation, and then you detect subsequent decays. So you know, so these 4 alpha decays that I was talking about, or 5, we know that they're happening, and we know that they're happening at, let's say, microseconds apart, and we know that they're happening in the same small pixel of our detector. So that's the trick. The trick is to make sure that we both know that, okay, they happen in exactly the same place immediately after each other. So actually the fact that it's quick makes it easier to do. It just doesn't, as long as it's not too quick, but microsecond is manageable. Nanosecond, billionth of a second would be very tricky, but millionth of a second or thousandths of a second, that's absolutely doable.
Okay, well, we just at time. There was quite a funny question that I thought I'd just ask you as the last question. Could someone technically convert all energy into mass and vice versa? Would cloudy with a chance of meatballs be possible with a large amount of energy? Have you seen cloudy with a chance of meatballs?
No, I haven't.
So they basically they can convert with enough energy, they can convert matter into anything. So he basically turns the weather into food. So could you turn with enough energy and mass, could you turn anything into anything else?
In principle, you could, right? Because if you could convert protons to neutrons, you could convert neutrons to protons if you've got enough energy, and you could combine them into another isotope. So yes, I think in principle, you could, and indeed that is the transmutation that Rutherford started off in 2019, right? And that we saw from 2020, 1919, obviously. 2019 is a bit more recent. 1919, when the first transmutation, that was exactly what was happening. They were taking one thing and making it into something completely different, right? If we only had nitrogen in the world, we could make oxygen in this way. Right.
Well, there you go.
Yeah, it's a long way from there to making food or something that's more useful. But I mean, oxygen is useful. I have found it very useful during this hour.
As we all do. Well, there's a challenge for the next generation of scientists to be able to create food from weather like cloudy with a chance of meatballs. Well, okay. We have reached time, so thank you very much, Christian, for your wonderful talk and for answering all those diverse questions. Thank you, everybody who's participated and asked the questions. All that remains for me to say is, again, thank you for joining us. Thank you to Christian for giving a wonderful talk and answering all those questions. And I wish you all a pleasant rest of your evening and hope to see you next week. Thank you very much.